4 o'clock. It's time to get started. It is a pleasure to introduce Gerry Gilmore, who's visiting us from Cambridge University, where he's a professor. Gerry is a fellow of the Royal Society and was a recipient of the Daniel Challenge Medal in 2013. Gerry has worked on many topics related to stars and stellar populations in the Milky Way, including measurements of the low mass initial mass function, studies of the thick disk of the galaxy, the local dark matter concentration, the discovery of the Sagittarius dwarf galaxy, and he's a co-PI of the Gaia-ESO Spectroscopic Survey, and he has been deeply involved since the beginning, or even before the beginning, of the Gaia survey, which I think he's going to tell us a lot about today. So with that, take it away.
Thank you. Good afternoon, everybody. It's a pleasure to be here and tell you a little about this remarkable project that I'm fortunate enough to be part of. So this rather crowded slide gives you a brief overview of the whole thing. So inside there is Gaia. It is launched. It was launched end of 2013. It's in operation, and it's producing 3 complementary types of data. The bulk of it is fundamentally scanned imaging, from which one can measure photometry and, critically, astrometry. In addition, it's measuring spectrophotometry, so here's some Gaia data. So this is new. We've never had this in astronomy before for everything. I'll come back to that later on. And there's also a spectrograph on board giving proper spectra for the relatively bright stars. And the tagline is 1 billion pixels for 1 billion stars, because the Heart of Gaia is a 1 billion pixel camera, the largest camera yet built and put into space. And the goal was to try and do an unbiased survey of 1% of the Milky Way galaxy so that we could deduce the global properties on the big scale. So what I'll do is give you a brief introduction to the background and the science of what we're doing, then to Gaia itself, and then show you some of the things that are coming out of it. So the context is something that many people in this subject will know, is trying to understand the 3D structure of the Milky Way that's in the background there. And the first big step in modelling was made by Isaac Newton, and here are his notes from his second edition of the Principia, and as you can deduce, they weren't published. Newton produced his books by writing the text in Latin perfectly, in complete final copy, and leaving spaces for the proofs and the diagrams and the tables and so on of numbers. And he was a smart enough person that they all did fit, and sure enough, he would fit things very well. But you can see what happened when he came to fit his model of the universe. And so the information he had available was star counts, all the way back from Ptolemy in the ancient catalogues. And when he compared his model to star counts, you can see what happened. So like all Cambridge professors, both Cambridges, and theoreticians in both Cambridges, he immediately said, well, my model can't be that bad, there's something wrong with the data. And so adjusted the data as much as he could. Along the way, one of the first steps he did was to deduce that the magnitude scale we use in astronomy is actually logarithmic. And so he deduced that our eyes are logarithmic, which is an interesting, shows how smart Newton was. And what he was trying to do was cheat, and he ended up with quite a clever thing. But eventually, he gave up completely and couldn't make it work. And like all true theorists, he could not believe that the universe didn't match his simulation. And so he, in fact, gave up astronomy at that stage and went off and became a banker. About a century later, the first real progress was made by these 2 people, the Herschels, Carolyn and William. And they went out with a telescope and actually did what the average person on the street thinks astronomers do, and looked through telescopes and counted stars. Phenomenally boring way to spend your life, but anyway, they did it. And through a very clever inversion process, which really was quite smart, deduced that this must be the structure of the Milky Way, and so at least it showed it's got a disk-like and so on. And this is not far wrong. So this was the real progress. And this was possible, of course, because Herschel came in from a completely different background. So he wasn't a rigid authoritarian Catholic the way that Newton was, who could not conceive of the fact that God didn't produce a perfect universe. And he came from a background as a musician rather than a mathematician, and so he just said, well, I'll believe the data. And Carolyn was, of course, the great data person of all time. So anyway, they came up with this, and much else, actually. If this article is worth reading, it talks about extragalactic galaxies and how many other planets there are and all sorts of stuff, all of which he was so far ahead of his time that no one took any notice of. But now what we want to do, of course, is go and get the 3D data to analyse what's going on in the universe. In fact, we want to go beyond 3D up to about 12D. So this is the information we wish to collect about the stars in the Milky Way so that we can go beyond projected views into 3D views. You can see on the screen here, this is an illustration of parallax and proper motion. I wasn't going to put this in, but I was reminded by my host that there are people in the audience who do theoretical cosmology, and I really should explain what a parallax was. So there it is. But in fact, this is what we're going to try and deduce from all this information down here, these fundamental three-dimensional properties of the galaxy, but not as a snapshot. The goal is to do dynamics. So these are the kinematics which we measure, and the goal is to do dynamics. And here we are. This is a snapshot from a movie. So this is our modern picture of the sky from the Gaia data release from a few months ago, from April. And so there's about 1.7 billion stars on there, the majority of which are located in 3 dimensions in this picture. And I'll come back later on to what that is. Because there's such a lot of there are so many pixels in an image like this, it's quite hard to show the information content of it. So I've got 2 zooms. There's one. So those two are the H and Chi Persei, the open cluster pair that the observers among you might recognise, or you can see them by eye. And you can see this is what happens when you look deep in such a field around it with some extinction maps and so on. And there's one done using Gaia colours, again showing, I've forgotten the name of it, some famous cluster or other. And all the effective dust and extinction and complexity and so on. Which, but this is just a taster of how much information is out there, except it's even in time domain as well. So now let me give you a little local context to this stuff. Of course, one of the many ways in which one presents information about stars is through the Hertzsprung-Russell diagram. A lot of Cambridge connections going on here. So here's the original, the first ever publication of the Hertzsprung-Russell diagram, which actually dates from 1920. People were talking about this thing for a decade before anyone got around to publishing it, and this was a review article in PASP by Russell, and it was the first time it actually came out looking in this modern famous Y fashion that we have. And here's the Hipparcos one. So you can see the basic picture there was fairly reliable and took 100 years to do better, which is this one here. And so, but there's an interesting background story behind this, which sort of puts it slightly in a little more context. And where did the Hertzsprung-Russell diagram come from? Well, Hertzsprung, who was working in Potsdam and Leiden, had discovered that some red stars were giants, and that's why his name was on it, but that was what he did. But the real requirement to make progress was to measure parallaxes. And measuring parallaxes became possible only when there was a huge technological revolution in astronomy, and that was the discovery of photographic photometry, so stellar photography. So this became clear that it was actually possible to do industrial scale measurements and also precision measurements in the lab from a photograph rather than by eye at a telescope around this time. And so the new professor in Cambridge named Sir Robert Ball, who was a quite famous person of the time, when he got the job in 1893, he said, right, we're going to do state-of-the-art work into stellar parallaxes. And so the typical history was this thing. He said, right, I want a new telescope. Well, they ran out of money. They set up a committee. Nothing has changed in the last 100 years. Eventually, they got the money from a philanthropic donor. And the interesting thing about this story, the special thing, is the philanthropist was Anne Sheepshanks. This is called, she was one of the first ever Victorian women philanthropists supporting science. And she's forgotten. In the sense that people don't remember the name Anne. She gave the money in memory of her brother, who was an astronomer, but it was her who gave the money, and people think it was him. It wasn't. It was Anne Sheepshanks. And this is the telescope they built, funny looking thing, but they built this was the first proper stellar parallax machine built for that, and it's not there anymore, got knocked down in the 1960s. But as well as that, they developed a precision measuring machine. And all this work was led under the scientific supervision of Robert Ball by this bloke named Arthur Hinks. And he was the person who designed and built the precision measuring machine, set up the parallax program, made it brilliantly successful, and was diverted for a few years by the newly discovered bright asteroid. I think it was either Vesta or Ceres, which people realized could be used to measure the astronomical unit. And so they put a big program into measuring parallaxes of this asteroid. And he became famous for that, leading that work and succeeding in nailing down the scale of the solar system. And then he moved on to stellar parallaxes, the main program, and went on for a decade or so. It was all led by Hinks and was all set up by Hinks. And then rather late in the process, the young Henry Norris Russell was in Cambridge recovering from illness, and he recovered quickly, came along to the Cambridge Observatory and said, "I'm bored, can you give me a project, please?" And they said, "Oh, we've got this work that needs to be written up on Cambridge parallaxes." And so there's some interesting letters where the people in Cambridge said, "Well, we'd love to hire you, you've got no money." So they wrote to the Carnegie Institution, and all these letters are still in our archive saying what a promising young man he was, and the references to Norris, to Henry Norris Russell from all the observers he's around in the US, writing to the Carnegie Institution saying he's worth the money and so on. All the original references, they're all still there in our library. And they got the money, and so Russell stayed there for a year and ran this program. Near the end of the time, this is a classic example of how postdocs end up getting all the credit for their supervisor's work. Is why I'm going on about it. Near the end of the time, Hinks, who was leading the program with Russell as assistant, left. And he resigned in protest because he hadn't been promoted. So they needed a director. A new director came in, and they hired a new director and appointed him. And Hinks said, "This guy's not remotely as good as I am. He's not in my league. I want that job or I'm leaving." And they said, "Sorry, we've appointed this new person." And so Hinks left. He left astronomy, in fact. He moved into geophysics, and he became very distinguished in geophysics. But he just walked away. And of course, the new observatory director that he thought was a second-rate person was Arthur Eddington. So, touch and go. But apart from that minor sort of personality glitch, we would probably be talking about the Ball-Hinks HR diagram, but we're not. So there's an interesting sort of historical connection between our two observatories. Now this is another example of what comes out of it, just to show you the examples. This is the Gaia-Hertzsprung-Russell diagram. This is just for nearby stars with very high quality data, so all the junk is gone. And you can see the main sequence, the binary sequence, all this sort of turn-off structure, the age structure, and down here the white dwarf sequence. That's all new, and zooming in you can see the binarity of the white dwarf sequence, the helium white dwarfs and the hydrogen white dwarfs, and again that's the first time. So there were a handful of white dwarfs with good parallaxes before that, but now you've got this complete structure allowing one to map the history. And here's the binaries up here and so on. And here's another illustration. These are some old globular clusters using again just Gaia data. And you can see how they stack up with metallicity and the different horizontal branch structure and RGB structure. And so all our preconceptions are resolved, as even all the blue stragglers and things. So that's where we are. Now, where did this come from? So here's just one slide on the early history of the project. And it started in the early 1990s, where there were the regular few-year proposals for projects, and one of the proposals came in was called Roma. It was a successor to Hipparcos, a big Hipparcos basically. Came from this little group of which I was involved. And at the same time, the European Space Agency said, well, we need to start getting ready for next generation interferometry missions, imaging planets, gravity waves, all this sort of stuff. So we wanted an interferometer. And so this thing called Gaia was put in as an interferometer proposal for the Cornerstone. They're the big ones. And so these two proposals were merged into a science study where the study of the interferometer option lasted for about 3 months before people said this is not a smart thing to do. But the politics had been won. Once you get in the queue, you never get out of the queue. So that's a nice example to remember. If you're proposing a mission, you've got to provide the answer that the agency wants rather than the one that you want, and then you'll get to do what you want with the money afterwards. And so then a little science team was set up. Worked for the rest of that decade producing the detailed proposal, which is called the Red Book in ESA jargon. It was published down here in this famous article, and these are the people on the science team. Then in 2000, just on 18 years ago, there was a presentation, almost exactly, and these were the presentations of the proposal to ESA for adoption. So you see, I was one of the people saying, why should Gaia? And I'll show you a few of the slides later on from that proposal saying what Gaia was going to do, so you can compare what actually happened. And so this is the timeline of the proposal. It takes basically 2 decades to go from getting the work started to when you've got the data in hand, and it costs you €1 billion. And a lot of us have gone grey in the meantime through that process, but we're very fortunate to be involved in it. And so this is one of the slides I showed 20 years ago, 18 years ago, saying what we were going to do. So this is the summary of Gaia. I'm not going to read it all. You can read the bits you're interested in. But basically every single one of these things has turned out astonishingly accurately to what we're actually doing today. It's very rare, actually, as anyone knows, when you're doing state-of-the-art instrumentation to actually end up doing what you wanted to do. But this has been really remarkably accurate with what we've done, and similarly beyond the galaxy. The heart of it was the galaxy, because remember, in these days no one had thought of dark energy or anything like that. Words didn't exist. Though in fact the same science case is in there. And then there's all the sort of relativity and local extragalactic stuff. And then the units of these things are sort of interesting. So we're talking, if there are any engineers in the audience, the scale of accuracy is picoradians. No one knows what a picoradian is unless you're an engineer. And so the analogy that we came up with was a human hair at 1,000 kilometres. But no one's got the slightest idea of how thick a human hair is. And so they came up with another analogy of 2 centimetres on the moon, which was very popular, but it turns out no one's got any feel for how far away the moon is either. And so a more useful analogy is that this is equivalent to measuring the thickness, not the width, but the thickness of a fingernail across the Earth. And that's the accuracy of each Gaia measurement. And there are a lot of measurements. Now the way that this works is by having space astrometry, is by having 2 telescopes. So you've got one down one line of sight this way. At the same time, you've got a second line of sight out here, and you just scan around the sky, and eventually you map out the entire sky through those 2 lines of sight. I'll show you why 2 in a moment. And this is the heart of Gaia. It's just an optical bench. It's in principle very simple. It's an optical bench with 2 telescopes hanging on it and a focal plane down the bottom. I once foolishly was in the media saying, oh, Gaia is really fundamentally a very simple thing. It's got no moving parts. It's just a single optical bench. And about half an hour later, I got a phone call from the head of the Science Operations Centre saying, how dare you? This is the most complicated mission we have. Everything's got to be controlled to ridiculous precision and so on. But in principle, it's simple. And in fact, it's simple in many ways because it's all made of the same material. So everything's made of silicon carbide. And this is the first large silicon carbide structure ever built, and that was why aerospace people were keen on building it. And so now it's the heart of all next generation big missions because it's so stable. And to keep differential flexures and things down, everything is, the mirrors and everything else is silicon carbide as well. Now, why are there 2 fields of view? The answer here is to try and get the difference between narrow field relative astrometry. So if you look through a normal telescope, you can measure these little I've suppressed proper motions just to keep it simple. You can measure all these little parallactic ellipses, but they're all lined up the same way. And so you've got no 0 point in this. You can measure differential, as this blue line shows you. You can measure differential distances between 2 stars quite accurately, but you've got no 0 point. So you have to have something in the field of view that doesn't move, or whose distance you know, and so it's always model dependent. But if you've got 2 telescopes with a known angle between them, then you get 2 ellipses which are not parallel, and therefore you can measure this distance, and you've got an external measure of this large angle, which should be about 90 degrees. But you have to, because you know that independently, you can actually measure this large angle only by measuring locally a small angle, and that's the way it works. So you have to know this angle very accurately. It's called the basic angle, and then you can solve this for real parallaxes, and that's something you can do only in space, and so it's why astrometry is done in space, where it's much more expensive than anything else. So here's Gaia. There's a little pig cartoon of what it looks like. It's out at the outer Lagrange point, exterior to the Earth, so 1.5 million kilometres out, moving in this big halo orbit. It's not actually sitting at L2, it's in this big halo orbit around L2, so it never gets in the shadow, keep everything thermally stable. And this is where the next generation of everything's going. So Planck was out there, JWST is going out there, and so on. You can see it. JWST is probably going to be a lot brighter. Gaia is about a 20th magnitude. Because it's at L2, it's always close to the equator at local midnight. So you'll always know where JWST is if it gets there. And you can always go and see Gaia. And so it's tracked from the ground as part of the requirements on precision, which I'll come to in a minute. So the heart of Gaia is this camera. This is really what makes it special. So this is a 1 billion pixel camera. It's 1 meter long, 1/2 meter wide. So each of these CCD arrays is the size of the palm of your hand, and they're all state-of-the-art things. And so this bit, these two strips detect the stars as the stars move across this way. They do the detection and clocking. And this bit measures the broadband imaging to do the astrometry and the photometry. These two strips down here, that one and this one, have prisms in front of them, so they measure spectrophotometry, and this bit has a spectrograph in front of it, so it measures the spectra. And so as the star goes across, all those things are measured every time. And to give you a measure indication of where we are, these are the current photometric accuracy derived from this stuff for the first data release and the second data release. And so you can see already for brightish stars, the photometry is down at better than a millimagnitude level. And this is where it's supposed to get to eventually. This jaggedy structure, this won't happen. The very bright stars will never be very accurate. But this jaggedy structure is because of the way that Gaia keeps subdividing the integration time on the CCDs for brighter and brighter stars. And every time it does that, the star is illuminating a different part of the pixel that it is otherwise, so it has to be independently calibrated. And so these jumps and glitches in the calibration are things that will go away with time, but they're just caused by the fact that at bright magnitudes there just aren't enough stars on the sky to self-calibrate as accurately as there are at faint magnitudes. But anyway, you can see there's about 1.3 billion data points plotted on there. And for the brighter ones, this is quite decent accuracy, actually. And even for the faint ones, this is 1% photometry up here. I mean, us old-fashioned ground-based observers used to think that was okay. Nobody does anymore. And here's the spectrograph. You can see it's quite an interesting bit of technology. This is just the GRISM, but there's this just a GRISM spectrograph has a throughput efficiency of above 98%, which is pretty impressive because normally we get 20% in a telescope. But this costs more than an average spectrograph. But it's a nice example of the sort of precision and what's in here. And so here are the DR2, the radial velocities. So you can see they're all bright stars only, of course. You can see they're bright stars. But the velocity accuracy is way below the goal, which is 1 kilometre a second. It's already nearly 10 times better than that for bright stars. And as time goes on, this faint limit will creep across to about 14th magnitude soon, and then near the end of the mission to about 16th. But you get very few photons in a spectrum each time. So brighter than about 14th magnitude, we're not going to publish real spectra. They'll just be statistical velocities are all that's going to come out. And this is a map of the radial velocities projection on the sky. You can see large-scale galactic rotation, bit of solar peculiar motion, bit of epicyclic orbits and so on. There's a huge amount of information. And this is just for the bright stars. There will eventually, the velocities be about 350 million stars with velocities. So it's quite a useful little velocity survey, even apart from everything else. It's not bad, really. There's another one of my original slides from nearly 2 decades ago saying what's going on and how we're going to do it. Well, how do you actually get measure the data? What does Gaia actually measure? Well, what it measures is a pixel flux, actually a number of electrons, but it goes through an A to D. So you measure a pixel flux at a time. And this is all a spacecraft can actually measure. A spacecraft can't measure a position because it's got no grid. And if any position it did measure would be no better than its own estimate of where it is. And that's not accurate at all. So what one needs, therefore, is to turn this backwards and say I have a pixel flux at a time, and then you have to work backwards to say where is the spacecraft, what is its orientation, what is its physical structure, where are all the mirrors, all the way back through the optical path and the velocity path back onto the sky to see where it is. And then because we're talking things, accuracies of 1 part in 10 to the 12, you've got to worry about all the relativistic terms. So for example, if you've gone to just straight Lorentz contraction type special relativity, you need to know, to do things to this accuracy, you need to know the spacecraft velocity to millimeters per second. And this is orders of magnitude higher precision than has ever been done for any other spacecraft. Similarly, you've got to know where it is to a kilometre. And again, this is a whole new requirement compared to anything that's ever been done before. And you've got to know its spin rate to 1 part in a million, which again is not a non-trivial measurement. And you've got to know where the mirrors are, and so there's an interferometer. So you've got this basic angle thing. So there's an interferometer which measures the relative mirror locations to picometer level. And just to put that in context, this is much less than the size of a helium atom. So there's an interesting sort of engineering philosophical concept, is what do you mean by the position of a mirror to an accuracy that's smaller than the molecules that one on the surface of it. And so this all comes into the sort of relativistic modelling of things. But there's a level at which you have to do everything. Also, there's a point that people sometimes surprised by, is that you have to measure colours. As you say, they're mirrors, right? Why are you worried about colours? It's because the polishing error on a mirror, a good mirror, is typically of a scale which is comparable to the wavelength of light. And so the mirror aberrations that we tend to think of as just wavefront distortions are actually colour dependent. And so when you've got 5 mirrors, each telescope, they're 5 mirror anastigmats, so you get this very, very complicated pattern of colour dependence to the point spread function, depending on where you are in the focal plane and which telescope you've come through. And these are significant on this timescale. So this turned out to be the main limitation until last year, and it still limits the published data. And again, just to put this GR term in context, solar light bending at 90 degrees from the sun is 4 milliarc seconds. So that's 4,000 times larger than the accuracy we're trying to measure. So the largest significant signal measured in every Gaia measurement is actually light bending through GR in the solar system. Light bending by Jupiter is a 2,000 sigma detection in the Gaia catalogue at present. So, to take all these terms out, everything's got to be done in a full GR metric. It's quite an elaborate process, and you need physical models of everything. Just sort of fitting to residuals is never going to work. And so I won't read all this stuff, but just to show how we actually do it, we start when the raw data comes down and is fitted with a point spread function, and then a source is identified and then is matched to the last time that source was observed, so it's got a name attached to it. All the local electronics, the charge damage and so on is all corrected for. And so this gives a pre-processed source list. These come to Cambridge, where we do all the photometric processing and the spectrophotometric processing and measure colour and provide all the bootstrapping calibrations. And with that information then goes to the astrometric processing, which is sort of German-French data centre, where all the spacecraft attitude and the astrometric parameters for every source are put into it. In parallel with that, the radial velocity measurements are measured, because for nearby stars, perspective acceleration is important. So you have to know the radial velocity to get the data fit. And then all this stuff is then put back together and iterated back to improve the point spread function that you started with, and the corrections and so on, and you iterate till convergence. And that process takes somewhere between a year and a half, and that's why it takes so long to get the data through, because just right now we're processing the data for the next data release in Cambridge, and even though I have a HPC system, which is about half the size of this room, state-of-the-art one, it still takes about 6 months. So there's a lot of data. You'll see why in a minute. And so what we actually have is something like 10 to the 13 individual measurements and about 10 to the 10 unknowns. And so it's not possible, with given computing, to invert a 10 to the 13 matrix. And so you have to do rather clever iterative connected systems. Most of those unknowns are the astrometric parameters of the stars, but there are a few 100 million associated with what I just mentioned about turning a time into a direction on the sky. And so all of this stuff's got to be solved for iteratively. And so it needs a lot of people. That's why you get things like that, and a lot of time. And so think of all those people whenever you use the data. Now, no mission is ideal or perfect. You have to live with the real world. I'm looking for a clock. Is there a clock? Ah, up there. Aha, right, thank you. Right, so I'm on time. So there are a few things that you've probably read about that were wrong. What happened? First, there's a lot more scattered light in Gaia. This is due to fibres sticking out the edge of the sunscreen. It was known they were there before launch. It was parts of the sunscreen that fold up, and you couldn't put protective tape around because they have to fold up to fit in the launch scudder, and there were a few fibres sticking out. And the electronics people decided at the time not to tell the optics people about this because they didn't want them cut off in case things went into the electronics, and this was too late to do anything about it. And so, but the rest of us got a bit of a surprise, but anyway, it's not a disaster. In fact, there's a more complicated problem, which is a few unbaffled stray light paths go straight into the M2 mirrors, which are about a degree in size. And these were not thought about in advance and were a big surprise. And just occasionally, because of course you're scanning across the whole sky, something bright goes through that degree, and then blast of scattered light goes all over the focal plane, and it's horrible. And particularly a bright thing like a planet, and that just messes stuff up. So this is just complicated. It's been partly mitigated. It hadn't been mitigated. It's been partly mitigated through mission extension, and partly through being very, very clever with the choice of windows on board. For the first couple of years, there was ice. This was known about. It's the carbon fibre is hygroscopic, and so although everything was clean when it left Europe, it's sitting on a rocket in French Guiana, which is in a swamp for a couple of days, and so it was expected to absorb about 1 kilogram of water, and it did. It took a couple of years for the stuff to come out, and of course it froze on the mirrors because they're the coldest thing. But knowing this was coming, there were heaters behind the mirrors, and so for 3 times the mirrors had to be heated up and recover this. That's all finished now. There's no more ice coming out of it. There's something that was discovered in Hipparchos, which is ubiquitous in spacecraft, and particularly in sun shields. You get these places where the local stress is relieving itself, and so you get little glitters and clanks. And so the spacecraft jitters. This is normally just put into guiding noise. It's what's called, not accounted for in normal missions. But for us it matters because it affects the spin rate slightly. And so this is this is going on all the time. This is an extreme illustration here, but this is going on all the time and has to be corrected for by tracking it out. And then there's another thing which is still not understood as how it happened, but there's clearly a radiative link from the sun side to the dark side of the spacecraft. There's a hole in it somewhere. And so in some way connected to the electronics to do with the communication system. And so heat gets into the system, and this is the basic angle oscillating. Fortunately, it's fairly smooth and almost periodic, but it's oscillating by a milliarc second, which is not a large amount in terms of angle, but nonetheless is 1,000 times the specification. But fortunately, we have on Gaia an interferometer, which was put on there basically as a reserve backup in case something like this happened. It wasn't really expected to be necessary, and turns out to be the highest precision, most stable laser interferometer ever put into orbit. And so it's measured. This is the measurements from that. I mean, it's astonishing. And so the mission was saved. It's possible to calibrate all that out. So those are the glitches. Just to give some idea of the precision, just very briefly, the other thing that happens with Gaia is it gets hit by dust. And so here's an example. This is the 3-axis spin rate versus time. Remember, this is what we need to invert to get positions on the sky. And here it is, and at this particular time, a dust particle hit Gaia, and this is a real transfer of momentum. And so the spacecraft around all 3 axes changed its momentum. When it got to here, the onboard system detected that something had happened, and so it corrected for it, and so it oscillated back down, and a couple of minutes later it was back where it was. In this particular case, by chance, the dust particle hit one of the thermal sensors, and so you could measure how much energy was dumped into it. And you can see it takes a day for a sensor to get back to normal when it's had little heat put. It just shows how sensitive these things are. But from that, it was possible to measure the orbit and work out what this thing was. So it's 50 micrograms. Now, 50 micrograms are pretty tiny, actually. This is about 1/100th of a grain of salt. And it was enough to do this to Gaia. But the onboard precision track guiding system, or correction system, it's called a micronewton because it works with micronewtons as well. And so the onboard propulsion system that corrects for these sorts of things actually fires microgram amounts of nitrogen out. And at that level, you have to know what sort of isotope of nitrogen you're talking about. But that's the only consumable we have on board, is the cold nitrogen system that corrects for these things. And so that's a routine operational thing. There's one other thing that's gone very well. Sorry, this is a little bit blurry. It turns out I'm not allowed to show you the real data properly for this, but this is radiation damage versus time. And the news here is very good. And so here is radiation damage in 3 different lines versus time. You see it builds up, of course. This was through the first year where the mirror was heated twice to get rid of the ice. And of course, a byproduct of heating a spacecraft is to anneal the CCDs. So you improve the CCD, you reduce the CTI damage. And so you can see after the heating, the damage rate dropped back right down to there. And then nature decided it didn't like this, and so immediately dumped a solar flare into the mission and completely undid all the good that was done by the annealing. And then precisely the same thing happened here. You see it went back down and then bang. And in fact, that happened a third time as well. So there have been 3 big solar flares. There was another one more recently where we hadn't done the heating. So, but 4 solar flares over 4 years is way below prediction. The sun's been really happily quiet, or disappointingly quiet if there are solar astronomers in the room. And so we expected to be up here in solar radiation damage by now, and we're actually down here. So it's a few % of what it should have been. And so the news is good in terms of lifetime and performance of the mission. Okay, so now onto what's some sort of science that's going to come out of it rather than that has, just to remind you of the parallax thing. So one of the things that, one of the potentially most interesting things that will come out of Gaia in the long term is planetary systems from astrometry. So what's shown here in the size of circle is the astrometric signature in micro arc seconds versus period for known planets from a couple of years ago. And you see these signatures are huge, and so every single one of these things is going to have a really, really good Gaia orbit, and that will provide not only the position of the planet, but the period of the planet, because you get, and the mass, because you'll know the inclination. So it's a proper astrometric thing. And it will also find things that, just from astrometry, that are transiting or not quite transiting. These ones you know the inclination, but it'll find a lot. So the current estimate, has it got up there? No. The current estimate is that Gaia will find in its extended mission, I'll show you a slide right at the end, about 70,000 planetary systems, for each of which it will give the periods and the masses of the planets. But from my perspective, not being a planet person, I think the much more clever, interesting thing is that because Gaia, this is going to be useful only out to 50 or 100 parsecs or something, quite nearby. In that time, Gaia will basically provide error-free distances to every star in that volume above some absolute magnitude limit. So you'll know precisely the parent distribution function from which all these planetary systems are coming. So you not only know which systems have planets, you know which systems don't have planets. And I think that's that's going to be a beautiful complement to the other, these other amazing missions like Kepler and TESS and so on that are doing things. So the combination. This is the first slide which says actually Gaia's great on its own, but put Gaia in combination with other clever things and you do really, really well. And so this is going to be interesting, and particularly because these are the nearby systems where it will be possible to follow up directly and see if they go green in summer. So it's the Large Telescope. There's another sort of solar system-y related aspect of Gaia, and that's asteroids, because Gaia measures everything on the sky. So these are real asteroid orbits. This isn't just a cartoon. It's unusual. The precision with which Gaia measures the orbit, this is a sample of, I forget, a few tens of thousands that were released early. The precision with which each orbit is known is about 100 times better than had been known before from the whole history of observation of these asteroid orbits. And that means that you can do things like orbit interactions. For the higher ellipticity ones, it will become a really good test of GR. And as we know now, though we didn't know when the proposal was written, quite a lot of these things are actually binaries. And so you can get masses for them as well. And so there's a lot of information coming out of all this stuff. And so only a sample has been put out now. Interesting ones are discovered in near real time, and there's a follow-up network where people, ground-based people, can follow it up, which not surprisingly is called FUN for Follow-Up Network. Then again, one of the original slides, there are all these, it's not just the galaxy. You see, I'm talking about the non-galaxy stuff. I'll come back to the galaxy, our big galaxy stuff. There's all these other things that will happen. This is underway. We are finding transients. There will be a lot more quasars found. They're turning up already. You may have noticed from one of the early results from Gaia DR2 was some apparently anonymous intermediate brightness, about 16th magnitude star that turned out to be the most intrinsically luminous non-lensed object in the universe. It was a redshift 6 quasar, and so things like that can turn up when you have parallaxes and so on. And then all the multiple lens quasars. It turns out there's a very large number of these in the Gaia data set that will become available, particularly in the next, it's more than that actually, particularly in the next data release. This was the prediction. And that's actually sensitive to omega lambda, but in fact omega lambda is being determined more accurately than we will in the interim. This is a light bending one, so this is, again, this was predictions for what is going to be done. Oh, these are Gaia observations of one of the Einstein cross, each little black dot. I don't even see them. There's little black dots there, each of which is a Gaia measurement of the flux and the position of the centroid, so you can do all the micro flickering. And on nearby systems, you can actually see the astrometry, see it moving as well. But anyway, so the light bending, to coincide with the centenary of the 1919 Eddington eclipse, there is a special experiment being run over the next year to measure light bending by Jupiter. And this is interesting because Jupiter is a subsidiary mass inside a dominant potential well. So you can think of it as moving. I know relativistically this is a funny way to phrase it, but you can think of it as moving in somebody else's potential well. But also it's flat and it's spinning. And so the high order lens-Turing type terms, which you can't get from the sun. So they are being measured. And so the main monopole term, or quadrupole term of Jupiter light bending, the monopole term, is going to be measured at about the 2000 sigma level, so that'll be known very accurately. But it'll be it's a very difficult thing to do, but it'll be about 7 or 8 sigma detection, so real, but not a lot of significant digits of these lens-Turing terms related to flat rotating system. So that is opening a new field rather than giving you so many significant digits that's going to change everything. And then this was always the prediction that we're going to do this. I showed briefly at lunchtime. I'll show you just briefly again. This is this thing that makes you ill. This is what the sky actually looks like in gravitational waves. Now, I'm not going to go and spend too much time explaining this. What's actually changing here is our local space-time. So we're not actually seeing the stars move. They're all too far away, but we're seeing the high-order distortion of our local space-time mapped onto the sky, and you can use that, of course, to test GR. And so this is the predictions that you can do with that. So let's start down at the bottom left here. These are the polarization patterns from standard GR, the plus and cross TT gauge polarizations. So they're the ones that are being tested straightforwardly. Then this is a scalar one, and these are longitudinal and tensor ones. So these are non-GR ones. And they can all be tested from this sort of pattern of what's going on. And the current calculations for where we're at, these coloured lines here are the current results from the various pulsar timing array experiments. And this is roughly where Gaia is going to be. That will extend to the left a bit and probably come down a wee bit and extend to the right a bit. And this bit in here is perhaps the interesting bit, because this is where normal inverted commas supermassive black hole binaries resulting from galactic mergers will be living. And so there may be something interesting to see there. You need to go about 1 more magnitude off in frequency, which Gaia certainly can't do, but pulsars might, before you get to the background radiation left over from the Big Bang. And that's a couple of orders of magnitude lower down in sensitivity as well. So it's an interesting, its real value will be to provide confirmation by jointly analysing the pulsar timing in Gaia data through that period. Another thing we do, I said in the beginning, finding transients. Well, this is the time sampling of Gaia. So this is just set by the spin period, so you get a time, repeated sampling on time scales of seconds, then minutes and hours and weeks for any patch of the sky. And so you find things that are variable. And so it's a useful time domain system. It's not optimized, and we can't steer it to look at a particular place. But it has the advantage that one gets photometry, astrometry, and spectrophotometry for free instantaneously. So if there happens to be something in the line of sight that is interesting, then there's no trigger delay. You get all the follow-up instantaneously. So Gaia is providing its own follow-up of everything it does. And this is where it's at so far. So these, as of a couple of days ago, these are the 4 big surveys of transients from the TNS survey. And you can see the special feature Gaia has, especially in these days when Zwicky is going to dominate up this bit of the sky and so on. But Gaia is dominant at low galactic latitudes. It's the only one of these surveys that's able to be reliable and quantifiably complete at low galactic latitudes. And so it has a lot to contribute down here. And here's one example of the things one is finding. So this is a binary microlens star. There's the usual complicated high amplitude, but you can see this is 13th magnitude. This is bright, these things. So Gaia's finding these bright things. But the interesting thing that's illustrated is not so much microlensing light curves. You've probably seen those before, but astrometric microlensing. And so you can see that this thing moves around. These grey squares are actually placed where Gaia did observe this system. So these are real measurements that we haven't got yet, but will appear in the next data release. And so you can see it's moved by 3 milliarc seconds. And this is a bright source. And so this astrometric measurement is going to be known to very high precision and provides a completely new form of precision analysis of microlensing systems. And in fact, we anticipate finding things just from microlensing which would correspond to free-floating black holes. So people are starting to look for that as a whole new discovery space for things that you can't see, but you see move. Another thing people ask about a lot, which is an illustration of the limitations of what you can do with Gaia data, is this is the local dark matter density. This is the value, a function of time from a couple of review articles there. And you can see what happened is since this Kuiken and Gilmore survey back in 1990, the numbers haven't changed at all. And so this was based on photographic photometry. And one wonders, well, you know, surely there's a lot of money being spent on trying to find dark matter. Surely we must be able to know its properties better than we knew in 1990 from photography. But the answer, surprisingly, is no. The reason being that to determine a dark matter density, you use Poisson-Boltzmann equations up here. The only relevant term, these are small correction terms at the few percent level, they don't matter. This is the dominant term, and it contains two bits. One's the velocity dispersion profile as a function of distance from the galactic plane, and that changes by a factor of 2 or 3 over the whole kiloparsecs range here, so this is close to constant. And so it's really just the logarithmic density law determines the mass density. And so what's plotted here is 2 different direct determinations. It tells you down here, yeah. So the red data points that you can see down here are the Sloan data curve. The green ones that you can see down there are my old 1980, 1990 ones. And the blue one is a Gaia distance data set. And the underlying black ones are a Bayesian inversion reconstruction of what the true underlying distance law is. And you can see there's these red lines are the lines. So that red line there is the original fit. It's the same fit we get now. That's the original fit that Gilmore and Reed came up with in 1983. So the numbers, now that was photographic, so I like to think I was careful, but you might well think I was lucky. But the point is the numbers haven't changed, right? So neither is the answer going to change. And so to do any better, you'd like to come in here. But in here is where all that time-dependent structure is being discovered. And it must be possible to identify some subset of the data in some rational objective way that is in kinematic equilibrium with a potential, and then you'll be able to do better. But until that's been done, and that's not going to be easy, we're not going to do any better. So now the last part of the science case I'd like to do is say, okay, so Gaia is again to emphasize the point we need more than Gaia. Gaia's cool, I'm quite proud of it, but not enough on its own. So Gaia will get us up to 6 dimensions in phase space for relatively bright things, brighter than 16th, a mere 1/3 of a billion, something, not really enough. So what you like to do is go up to much higher dimensionality, and so put in precision abundances. And from that one can get ages and histories and multiplicities and things. And so I'll give just one example of why this is interesting and why it's hard and why a lot of work is going to be required to really get complementary work to get the data results out of Gaia. So what I've got here on this messy looking diagram, let's start up the top left here. So this is a plot of the ratio of magnesium to magnesium to iron versus iron to hydrogen along the bottom here. for planet host stars. So these are the bright nearby stars with ridiculously good spectroscopic data. And you can see the magnesium to hydrogen abundance. It's just chugging along nicely at solar for all these stars here with a very, very small scatter. And so right down to half solar to twice solar, there's nothing happening. So you might ask yourself, well, hang on, where did all these twice solar and 3 times solar stars come from? They clearly didn't form anywhere near the sun because the interstellar medium near us is solar, and the gradient in terms of dex per kiloparsec is at the 10th level. So they can't have formed within 5 or 6 kiloparsecs of us. They must have formed further away, so they must have formed the very centre of the Milky Way. It's the only place where such metal-rich gas has ever existed, to the best of our knowledge. And so you can go in and do spectroscopy of galactic bulge stars and say, how do they tie on? Now this is hard to do because you end up trying to compare metal-rich giants with local dwarfs, and that's hard. So, but there is a special set of normal bulge main sequence stars which occasionally are microlensed and get very bright, and so you can get good spectra for them. And that's this study here. So again, here's magnesium to iron versus iron for these super metal-rich stars. And see, they're sitting up there at about plus 0.1 dex, whereas these are sitting down here at minus 0.1 dex. So are they the same, or are they not? Or is this just calibration errors? They're all the same sort of stars. They're all sun-like stars. But this study would tell you that these stars didn't come from anywhere in our Milky Way, which sounds ridiculous. And so the assumption is that you can't actually draw any astrophysical conclusions to understand your errors better. Here's another example of the same thing. Again, magnesium to iron. Look at this panel up here for stars that are very well studied because they're Kepler stars in a narrow solar twin type regime. These are very local. And you can see there's this spectacularly tight correlation between age and element ratios. Now this is the entire history of the galaxy, right? And so these stars up here, which are the super metal rich stars up here, these same ones, presumably formed in the centre of the Milky Way 8 billion years ago, and somehow know precisely where the sun is, and that they're going to the interstellar medium is going to resolve precisely onto the local, these stars which form locally, onto the interstellar medium 8 kiloparsecs further away from where they formed, given the entire history of all the different nucleosynthetic processes and all the different timescales and all the mixing processes that are involved in it. And it's even more extreme, something like yttrium. Clearly yttrium and magnesium just follow each other. So this is scatter of 1 or 2%. So you can use the scatter around this to actually look for anomalies that might correspond to planet hosts and so on. It's the same thing from apogee, except this scatter there is larger, so it's hard to do. So there's something really strange going on here. How is it possible that there is just no scatter in the element ratio versus time across 10 billion years and 10 kiloparsecs? Well, that's what Dave is telling us. So do we believe it? Do we not? Don't know. So this is just one. This is the only slide on this I'm going to show you. I'm going to stop in 2 minutes. This is one of the many surveys that are trying to do precision studies to follow it up. Again, it takes a lot of people to do a lot of work. So this I'm doing with Sophia Randich from Archetri in Florence, and here's some of the people doing all the work. This is just one. We all have this challenge of trying to understand what we're on. So anyway, back to Gaia. What's coming next? Last couple of slides, summary slides. What can we expect? What are you going to get next from DR3? Well, you're going to get very substantially improved astrometry. In DR2, our philosophy was actually set by myself and Tim Dezou in that early study in the 1990s, based on experience. So the only way to get your data thoroughly understood is to give it to the community and let them break it. And we persuaded ESA that this was a good thing to do, and for a mix of common sense and political reasons they agreed, and so it's still the policy that we're following. And so you get the data the same day we do, literally. But last time round there was only 22 months, and it's really hard to disentangle parallax and proper motion from that much, and so there's lots of systematics there. But next time round it's nearly 3 years, so it's going to be very much improved systematics. So from that it will be possible to actually get some orbital solutions from some fast-moving binary systems. There'll be lots and lots of radial velocities, probably go down to about 14th magnitude, so maybe 10 times more than what came out last time. For the first time there'll be average spectroscopy from the spectrophotometry. This is unique and new. In the whole history of astronomy, we've never had spectrophotometry for a large sample of stars. So we can actually start to say what they are. There's various stellar parameters will be divided, and I'm personally hoping that the community will instantly develop new and better ways of deriving these parameters. Source classifications, because from the spectrophotometry you can find emission lines, so you can discover quasars and galaxies reliably, and lots more variable stars. All this will come out in, the number is deliberately uncertain, but a good working number with a small error bar on it is Easter 2020, so 18 months from now. So you don't have too long to wait. This is just an example of the information content in spectrophotometry. So this is raw data. They're still not flux corrected. We still haven't worked it. We're still working on doing the flux correction. It's not that I'm not showing you the real stuff. We don't have it ourselves yet. But this is just an illustration of the Gaia spectrophotometric data on some supernova that Gaia discovered. And so you can see the change in the spectrum as it goes from the hot gas down to the nebula spectrum. You see the lines coming out of it and so on. And so just from Gaia data alone, you can see how much information you're going to get from the evolution of every variable source on the sky. In terms of accuracy, I haven't got Gaia DR3 on here. I just don't know how good that's going to be yet, but you can see the evolution of space astrometry since Hipparchus to Gaia DR1. Gaia DR2 is down about here. So this is parallax uncertainty in milliarc seconds. So there's 1 milliarc second. These down microarc seconds down here. So this is the newest prediction from just a few weeks ago, based on the data. This is not just a simulation. This is actually based on the real status of the data processing. So you see, we expect after 5 years, that's DR4, to be down by an order of magnitude from where we are now, and then do another factor of 2 better at the 10-year range. So this dashed line is a realistic prediction of where we'll be at the end of the mission. And you think, well, it's only an order of magnitude, that's hardly worth waiting for. But you can do better in proper motion even, where you get 2 orders of magnitude. So currently the end of mission prediction for where we're going to get with proper motions with Gaia is way down here at the 1 microarc second level. And so this is truly astonishing accuracy. And of course, what this will do, of course, is be perfect for finding all those planets. You'll see all the proper motions. So and even down to quite, moderately faint. So we're still doing 10 microarc second accuracy down at 17th magnitude. So there's a lot of stars there, and a lot of other things on the sky as well. So the future is quite bright, actually. Thing to remember is a lot of people work very hard to do this, so do put in the acknowledgements. And I'll just to end with where Gaia was a couple of days ago. So we recently passed our 1 trillionth measurement, our 7 billionth spectrum. Those of us who used to go to telescopes, just feel awed by these numbers. I'll leave it at that. Thank you.
Well, this is just absolutely magnificent. So thanks to you and to all those people. I have a question about microlensing. Mm-hmm. So you showed a fantastic event there, but of course most of the microlensing events will be only astrometric, and some of the astrometric signals are going to be very subtle. And so I think the challenge is really going to be to take the motions of stars that you're looking at, for which you have parallax, for which you're measuring a proper motion, but there's something a little wrong. And that something that's wrong is that there happens to be a dark foreground object. Could be a free-floating planet, could be a neutron star pair, or something like that. Mm-hmm. So at this point, what are the plans to do the analyses that could find those types of things?
You're exactly right, and that's a general example of many different analyses that will need to be done. Sorry, should I repeat the question for the video, or what's the pro forma here?
I'll be good.
You're okay? No, you're saying no up there, right? So you're exactly right. And in fact, it's the same thing for saying, is there a planet in this system? Because if you've got a long period planet, the planetary deformation will be soaked up by an incorrect proper motion. So the thing we tell everybody is that if you want to do proper science with the Gaia data, you have to wait till we release all the epoch data, and then you have to forward model what your question is onto the data and see what the answer is. Because when the Gaia processing is being done, every object goes through the standard 5 parametric fit, and if it's statistically significant fit, the Gaia iteration stops there and it goes on to the next star. And so you get a probably wrong set of astrometric parameters out for every object. That's the best one can do. And of course, so you then say, well, why don't you find the 3 sigma anomalies or something, until you then calculate how many objects do you get at 3 sigma from a 3 billion object catalogue. And then the answer is, sorry guys, you have to do it yourself. Okay, this is a proper statistical analysis problem. And so the Gaia project will deliver only things that require use of the entire integrated data set. Everything else, we give it to you. And so, you know, Gaia will produce a list of planets, and it will be grossly incomplete. It will produce a list of weirdo microlensing objects, and it will be grossly incomplete. And you have to find the rest.
Was that DR3?
No, that's DR4. DR3 is the first data release which provides full epoch data will be DR4, which will produce the full 5 years of data. And that's currently scheduled for, well, being real, don't quote me too loudly on this, being real is going to be 2023 rather than 22. It's about 5 years away. It just takes that long to process that much data. And that data release will contain 10 to the 12 pieces of information. And this isn't just numbers in a catalogue. Each of those 10 to the 12 things will be a probability distribution function with an error correlation associated with it. So you get 2 times 10 to the 12 matrices is what you're going to get if you really want to look at the Gaia data. That's what happens when you measure a trillion things. There are negatives as well as positives. But yeah, it's the same reason I told the Russell story. There's a whole world of postdocs who are going to go out there and get the science out of Gaia, while people have long forgotten what I did.
Charles? So you mentioned some large number, I forgotten what it was, of, I think mostly main belt asteroids that have been detected.
Yeah.
Are those principally objects that are already in the known databases and
Yeah.
better data, or,
Yeah.
or is there a significant fraction of new detections?
Both is the answer. The ones that have been released so far, there are very few new ones. The only new ones that are being released are ones that are obviously on unusual orbits, and so they needed to be followed up immediately. And that aspect of the data releasing is about a year behind schedule, and so they started that asteroid release system only a few months ago. And so the first data release was just to keep people interested, and there's only a few tens of thousands of asteroids, almost all of which are known main belt asteroids. The other interesting thing about Gaia is because it's out at L2, it's beyond the Earth. It's actually looking back at asteroids that are potential Earth crossing ones that live interior. Their orbits are interior to the Earth, so they're visible only in daytime. The Gaia can look, in fact, it looks back into Venus. You should see the mess when Venus comes through the focal plane. Yeah. But anyway, so Gaia sees all the way back into Venus, and you keep looking into that strip between Venus and Earth for 10 years, you'll pick up all the stuff that is sort of waiting to destroy us. But we don't know that stuff yet. They found it harder than they thought to find these moving objects.
Hi. First, I'd like to make a comment, and I'd like to ask you this. First, the comment. Superb thought, and I'm sure I'm not alone in greatly appreciating your sense of humor. After the question, why are you pointing at Charles?
I'll tell you the story later.
The question. Back in Hipparchos days, there was a determination of the direction of the Hyade drift. Mm-hmm. And that was statistically very significantly different from the VLBI determination.
Yep.
And I was wondering how Gaia will resolve this issue.
It didn't resolve. First of all, thank you for your comment about amusing. The explanation for the look there was that when asked how I would like to be introduced, I said you can say anything you like about me except the fact that I'm funny. Because I once was introduced in that way, and of course the audience was so disappointed. But anyway, the answer is that the VLBI result was right. The Hipparchos number was wrong. Gaia now knows the distance to the Pleiades such that there is, I forget the precise number, but there's something like a 25 sigma determination of the 3D structure of the Hyades now. So there's no longer any such thing as a distance to the Hyades. We have distance as the individual stars. And so there is a little video I could have shown of the 3D structure of the cluster. But we've looked into it, and no one has any understanding of what went wrong with the Hipparcos reduction. No one's, to be honest, had too much time to look at it. But Floor van Leeuwen, who did the original one, and I went back and we went through everything that he did, and we can find no explanation for what was wrong. It clearly was just wrong. And every measurement since in Gaia has just said, well, okay. And it's a good warning for Gaia. There'll be things in Gaia that are wrong that we don't know why either. So it's an interesting historical lesson to VLBI people. Have faith.
Well, I never had any doubt.
Is there any project that you're interested in redetermining the map of extinction in the halo of our galaxy?
Yeah, I should.
In particular,
yeah.
in 3 dimensions.
Yeah. One of the byproducts, I think the first version of it will actually come out in DR3, so in 18 months' time, is a new 3-dimensional extinction map based on a line-of-sight extinction to every star. So it's one of the parameters that's fitted, only down to 18th magnitude, so it won't go way out into the halo. But so it'll be a new 3-dimensional extinction map with a spatial resolution of a couple of arc seconds across the whole sky. And that will be 18 months away.
All right, one last quick question in the back.
Sorry, this is a less science one, but you said Newton was Catholic, and you ascribed his, liking for authority to say, okay, that was why he just decided that the data must be wrong. But I would have thought he was Protestant, because wasn't it not really allowed to be Catholic at that time of England?
That was a very astute question, actually, yes. People forget that he lived at the time of Henry VIII and Elizabeth I, and Mary, of course, the Catholic queen who came in between them. Newton started off as a devout Catholic and then remained devoutly conservative and never talked about exactly the details of what he believed in. And quite a lot of people in Cambridge and Oxford at the time adopted that policy to avoid being evicted from academia, because you had to sign up to the removal principles. But he did it sufficiently successfully, went off and became Master of the Mint, where he was particularly horrible and used to kill people for forging and things. But so he was successful enough. But certainly in his early writing, and in these unpublished letters that underwrite his cosmology, he had this beautiful cosmology. It's really simple, actually. It's just every star is equidistant from every other star. He just made this crystal. But it's such a nice thing to do. But of course, immediately people pointed out that under Newtonian gravity, that's dynamically unstable. So why did you do that? And he never got around to it. Well, he did, yeah. He called it God. He said, God, this is such a good universe, then God must keep it this way. And that's all in his letters, but he never published that. They were published by other people after he died.
All right, let's thank Gerry again.
Yep.
Who paid for all the
Sorry, thank you very much, but I have to go.
Okay.
Right.
Great to meet you again. Oh, yes, of course. You've already told me. Yes.
Go.
Yeah. Right. Okay. Good to see you.
Who
Yep.
paid for all the 400 scientists who worked on this? Did each scientist have to go back to his own or her own country and get money, or did he do it all? I mean, I'm thinking
The Spacetime was built because, unusually, it's the only one that ESA's ever done like that, as an integrated package built only in industry. And that's because the stability constraints are so extreme, you couldn't put other people's instruments on board.
right.
So ESA built the spacecraft and launched it and operate it entirely under their own funds.
You want to turn your mic off just in case you say something.
Oh, sorry. Yeah.
Off the record. Because you want to be off the record.
Otherwise,
That's a good point.
Hot mic.
Yeah, these things.
Out on the web forever.
Yeah, being like a politician. Where is it? Oh, yeah, if you can see it. It's beneath my line of vision. It's okay, I mean, just unclip it.